Hello everybody, welcome to Big Data Basics, an introduction to big data from the Alibaba Cloud Academy training team. I'll be your host for this section. I am Jeremy Peterson, one of the Alibaba Cloud Academy training instructors. We've broken the course into 4 sections, or rather, this section of the course is broken into 4 subsections: big data versus the database, batch versus streaming, data lakes, and then we'll talk about trends, where we look at some new technologies that are on the horizon in the big data space. So I want to start with a question. What is big data? This is a term that has a lot of hype around it. It's something I feel we should break down a little bit. So big data simply refers to a set of tools and techniques that are used to deal with large data sets. So the only difference between traditional data processing and big data is that the data sets in big data are too large to be worked with using traditional tools. So a traditional tool might be something like an Oracle database or a MySQL database. Big data is when you have to adopt new tools and techniques in order to deal with a data set that's too large to process using a traditional system. So when we think big data, we usually think of distributed multi-server systems like a Hadoop cluster. I should say that the term big data is evolving, and it now includes some things like techniques that are used for machine learning and AI. These things also count as big data now. Previously, it was just about storing and processing large data sets. Now there's an assumption as well that big data includes tools for visualization and gaining insights and training models. So there's more to it than there used to be, and the term will continue to evolve over time. The major problems that big data tools aim to solve include things like data capture, data storage, data analysis, search and indexing, data sharing, data transfer, of course, data visualization, data querying, and data maintenance. And I should say there's one that's not really in here, which is data insights. So you're trying to generate some value from the data you collect, perhaps by building predictive machine learning models, or perhaps by visualizing the data in a useful way that allows you to detect trends or get some insight from the data that you've collected. So when we're talking about big data versus a traditional data set, we care a lot about what we call the 4 V's. These are the 4 common properties that large data sets tend to have. The first is, of course, volume. You'll have terabytes or even petabytes of data, meaning that you need a distributed, scalable system to store, process, and index all that data. Then there's velocity. A lot of big data systems are characterized by the amount of data that's being collected and generated per unit of time. So the data is being collected at a high rate. If you think about something like Google search, or maybe Facebook or Twitter, the number of users that are online at any given time is in the millions. So each second that the platform is in operation, there are hundreds of thousands or even millions of events being generated. So each of those events is a data point, meaning that has to be processed and stored somewhere and indexed and made available for future use. So the velocity is high. The data is being generated at a very high rate. Then there's variety. Often with large data sets, you'll have data that's in different formats. Multiple systems are generating that data at the same time, so you'll be collecting the data from multiple places in multiple formats. Your data might include audio and video, as well as text, as well as IoT data, so messages from sensors out in the environment. So if you're a platform like, I don't know, Uber, or China's Didi or something like that, you're constantly collecting GPS data points about where your vehicles are located. Well, at the same time, you might be collecting differently formatted data about the orders that are going on, as people try and get a car. So you're collecting data that's in different formats. That's variety. And then finally, number 4, there is veracity. This is an often overlooked point, but it's really the most critical. Data is rarely perfect. There is such a thing as low-quality data and high-quality data. Big data systems often include tools and methods that are designed to protect the integrity of data and ensure data consistency. And also something that's very important when you're collecting a lot of unstructured data, like photos or video, is knowing the data lineage, where that data came from, and how it was generated. Those things might be important later when you go to process the data. So imagine, for instance, that You have video files that you want to process. It might be good to know the properties of the camera that generated that video. You might want to know where that camera is, what direction it's facing, who set it up, when it was installed. So you'll expect to have additional data about your data, which we call metadata, and that will be used to sort of keep track of where your data came from, how it's been processed and modified as you've worked on it and incorporated it into a larger data set. Data lineage is a big part of data veracity as well. So again, just to sum up the 4 V's here, the 4 major properties of big data sets. You've got volume, which means you have a lot of data. Velocity, you're collecting or generating that data at a high rate. Variety, you've got multiple data types. And veracity, you need to ensure the consistency and integrity of that data, and you need to make sure you know where it came from and how it has been modified or manipulated. Why is big data suddenly so relevant? The term is actually relatively old. People have been talking about big data at least since the early 2000s. The reason it's so relevant now and you hear so much about it is because of what we call the data explosion. So this is actually a chart I have borrowed from martinhilbert.net. The chart sort of expresses the world information storage capacity, roughly, based on the number of extant Blu-ray discs and hard drives and other storage media that are out there. So if you look at this chart, you'll see that starting in the early 2000s, there was a dramatic increase in the amount of storage space available, and also a decrease compared to pre-2000s in the amount of analog storage that's being used. So the amount of digital storage has really exploded and has started to supplant or replace a lot of the analog storage media that were in heavy use before the year 2000. And overall, just taking the analog and digital storage together, there has been a massive, many-fold increase in the amount of storage space available and in the amount of information being stored overall. So you can see it's been a pretty explosive change, and partly this has been driven by decreases in storage media costs. So the cost per gigabyte to store data on a computer has gone down dramatically since the early 2000s. You can now buy multi-terabyte hard drives to put in your house for less than $100. So we're at a point where enormous amounts of storage can be had for relatively little money. And that means that people are storing more data for longer than ever before, which is where we get this need for big data tools. You need a way to process, store, and maintain the integrity of these large data sets that people are starting to collect. So if we look at a brief history of data management tools, we can actually go fairly far back in time. This is not a new concept. People have been collecting and storing large data sets for a very long time, perhaps longer than you would imagine. The U.S. Census has been using punch card systems to tabulate records of U.S. citizens since at least the 1800s. So they've been using those types of systems for a long time. Electronic punch card readers have been available since the 1920s and were used for all kinds of demographic data collection in Europe and the U.S. They've been used by large banks. So we've had at least 100 years of data processing technology. Starting in the late 50s, you start to see magnetic storage, so hard drives. In the 1970s, as you can see on the slide here, you get RDBMS systems. These are traditional structured databases. So when you think of things like Oracle or IBM's DB2 or MySQL, those are relational database management systems, or RDBMSs. Most people just call them databases. So when you think of a database, that's what you're thinking of, a traditional database where you're using the SQL language to query, store, and manipulate data, and all of the data is stored in two-dimensional tables. That's a traditional database. We've had those since the 70s, and up until the early 2000s, if you wanted to store and process data on a modern electronic computer, that's how you did it. You used a traditional database. That did not start to change until the dot-com boom got underway. So with companies like Yahoo and Google needing to store extreme data sets, so data sets that are extremely large and difficult to process, then you start to see what we now think of as big data tools. So in particular, there's a big blue dot on my slide here that says Doug Cutting, Notch, right? That's 2002. Doug Cutting was a I believe, a Yahoo employee at one point, and in 2002 he started working on a parallel processing tool, a distributed processing tool for storing and processing large data sets. And it just so happened that at the time he was working on this, Google came along and released their GFS paper in 2003, which was a paper about how they were using large collections of traditional server hardware to store data in a distributed file system. So GFS is the Google file system. Not long after that, they released the MapReduce paper, which talked about how they were processing the data they were storing in GFS, also in a distributed, fail-safe manner across multiple machines. And of course, Doug Cutting saw these papers when they came out in 2003 and 2004, and he incorporated the ideas from GFS and MapReduce into Nutch. And that's actually where Hadoop comes from. So you may have heard of Hadoop. Hadoop was created out of Nutch. So Hadoop is the project that came out of Doug Cutting's work on Nutch after he incorporated the ideas from MapReduce and GFS. And Hadoop came out around, I think, 2006, and then they became an Apache project in 2008. So some of you will know Apache is sort of the de facto project manager for large Java-based open source projects. So if you have a large, interesting piece of Java software, often if you want to give it to the open source community, it goes to the Apache project. So Hadoop has been an Apache project since 2008. And of course, large cloud companies like Alibaba Cloud often will develop their own systems for data processing rather than use open source ones. So although Alibaba was using Hadoop for a while, starting in 2009, we began work on our own system called Feitian. Sorry for the Chinese on the slide. The English name is Apsara, but those two Chinese characters there, you can read those as Feitian. This is the system that Alibaba uses internally to manage its cloud platform. We've been working on that since 2009. It's still in active use and active development. This is the system that manages our virtual machines, our distributed storage pool, our big data analytics tools like Max Compute. They all run on Apsara. And we're constantly adding new features and capabilities to that. And of course, so are all of the other major cloud vendors. So is the Hadoop project. These things have to evolve with time. So I want to point out there are some pretty major differences between big data tools like Hadoop versus traditional databases. So we've talked about the fact that traditional databases like MySQL or Oracle don't work well at the hundreds or thousands of terabyte scale or at the petabyte scale. So why do big data tools work at that scale? What's different about their architecture? So on MySQL, for instance, queries are executed one by one, serially. And the reason for that is MySQL is going to run on a single server. It is a process or a collection of processes that all need to run together under the same operating system on the same machine so that they can communicate with one another. Hadoop, on the other hand, is built to run across multiple servers at once, and therefore it can execute queries in parallel, which means it can often return results faster for large data sets than MySQL can. Data in a traditional database like MySQL is going to be tabular. It will be structured as a set of tables, whereas data on Hadoop can be structured or unstructured, could be either one. Typically, Hadoop is going to use a distributed file system. In the case of Hadoop, there's a system called HDFS, the Hadoop file system, that's designed to store terabytes or petabytes of data across hundreds or thousands of machines, whereas MySQL is going to keep all of its table data in a single directory, essentially, on a single file system. That limits systems like MySQL to data sets typically less than 10 terabytes. Some commercial databases can go higher than that. A system like Oracle or PostgreSQL might be able to get up to 100 terabytes, but still there is a pretty strong upper limit because these systems don't scale across multiple servers. They're designed to run on a single machine. Compare that to Hadoop, which is designed to run on a cluster. It can go anywhere from hundreds of gigabytes up to hundreds of petabytes, which is hundreds of thousands of terabytes. So Hadoop clusters can get very, very big, and that's true of most distributed big data systems. I'm just using MySQL and Hadoop as examples here of the traditional database versus the big data system. So in a system like MySQL, data is going to be directly manipulated or changed in place, which is actually very nice. So when you're manipulating data in a table in SQL, you can directly manipulate that data. You can change it in place, usually immediately. So when you run a query or an update statement on MySQL, it's going to happen right away, usually within a second. Whereas on Hadoop, running queries takes some time. They have to essentially get executed as a distributed job that gets sent out to multiple machines, and then the results get collected. So queries will run slower. And then also on a system like Hadoop, you usually don't directly alter your data. What you'll do when you want to make a change is you'll create a new data set, and you will run your existing data through some type of a processing pipeline and produce a new copy of the data set that's modified in the way that you want. So systems that are designed for analytics, like Hadoop or Alibaba Cloud's Max Compute, they typically leave original data as is. If you want to modify that data, you do it by making a copy of it that's modified in the way that you want. Whereas in a system like MySQL, you can easily go back and directly modify the data that's sitting in a table. In a system like MySQL or Oracle, typically the tools for visualization and analysis are separate. They are third-party tools. They don't run as part of the database system. You would connect to your database from some other third-party tool like Tableau or something like that, and then you'd run your analysis in that separate tool. In a system like Hadoop or Alibaba Cloud's DataWorks plus Max Compute, you're typically going to have some tools that can run directly in the big data environment, so on the cluster. So in Hadoop, if you install visualization and analysis tools, they can run right on the same Hadoop cluster that's hosting and processing your raw data. So you can run them as a set, as a full stack that lives together, whereas with traditional databases, you don't usually run other workloads on the server that runs the database. Instead, you'll run those things somewhere else and then make a connection to the database when you need to pull data from there. So most big data systems are going to follow a workflow more or less like the one you see on the slide here, in which you're constructing what we call a data warehouse. So if you're using something like Hadoop or Alibaba Cloud Max Compute, you will be constructing a system, a workflow that looks like the one at the bottom of the slide here. You'll be using an ETL process, extract, transform, and load, to pull data in multiple formats from multiple sources. You'll then store that as a set of raw files or as a set of processed tables inside your data warehouse. If you're on Hadoop, the data gets stored in HDFS. If you're using Alibaba Cloud Max Compute, the data gets stored as tables inside of your Max Compute cluster. Once you've got that raw data imported into the data warehouse, then you will implement workflows that process the raw data. So you'll produce what we call summary data, which is data that describes the raw data in a more useful format. So your raw data might be, I don't know, perhaps CSV files that contain all of the orders from all of your stores around China or around Europe. You might then make a master table that has every order number and order amount and user ID. And then you would produce summary data from that, like sales per country or sales per region. That summary data table will also live in your data warehouse and will then be used to produce processed data sets that your end users will actually make use of. So they won't directly use the raw data, they will use the summary data. Your data warehouse is also going to contain metadata, which is data about your data. This will include things like what process was used to convert from your raw data to your summary data, where does your raw data come from, when was the raw data imported, etc. That would all be metadata. Those things in your data warehouse will be used to drive what you call a data mart and possibly one or more data services. So a data service would be essentially an API that you would set up that references your summary data, and then that API can be integrated into third-party apps that you build yourself to make that data available to your end users. Or the data could be going into a data mart, like you see on the top right-hand side of the diagram there. This is processed final data that you would put into a PostgreSQL or MySQL or an Oracle database that your end users can then directly query. You don't typically run end user queries on the data warehouse because that can be slow. Ad hoc queries that end users might want to run have to get converted into a distributed job and then run by your data processing system's scheduler, like the Max Compute scheduler or the Hadoop scheduler, if you're going to run them directly on the data warehouse. So typically end users are going to run their queries on a data mart that contains processed, exported summary data in a traditional database, because that database can return queries faster. So you'll have your end users talk to that data mart or to a data service API rather than directly to the data warehouse. But this is the general architecture that you'll be using in most cases. All right, so in the next section, we'll be taking a look at batch versus streaming data processing.